Hello everyone. Now we will present our paper Learning to Exploit the Sequence-Specific Prior Knowledge for Image Processing Pipelines Optimization. The configurable hyperparameters of various modules from any ISP aggregate to be a complex parameter space with tens to hundreds of parameters. Existing methods treat the high-dimensional parameter space as a global black box space for optimization and prediction all at once, while ignoring the inherent sequence of the ISP modules and the critical intercorrelation among hyperparameters. Inspired by the operating principles and structure knowledge of ISPs, we first propose a sequential ISP hyperparameter prediction framework. It is effective to introduce sequence information and similarity relations in the high-dimensional hyperparameter space. The model runs recurrently by predicting a group of parameters at each step. And hyperparameters groupings are determined based on similarity among parameters. We validate the effectiveness of our method in a variety of downstream tasks. Let's present in more details. First, introduce the definition of the ISP hyperparameter tuning task. On the left is the typical ISP structure. ISP is low-level image processing pipelines with some processing modules, each controlled by a set of hyperparameters. On the right is the ISP hyperparameter tuning task. These hyperparameters affect not only the output images but also the downstream tasks. It is important to find optimal ISP hyperparameters for different tasks. Recently, some automatic ISP hyperparameter optimization methods using downstream evaluation metrics come into sight. These methods include derivative-free or based on differentiable approximation gradient methods hyperparameters optimization, and methods that attempt to directly optimize hardware ISP hyperparameters in an end-to-end manner. However, existing methods treat the high-dimensional parameter space as a global black box space for optimization and prediction all at once, while ignoring the inherent sequence of the ISP modules and the critical intercorrelation among hyperparameters. Those modules with similar functions are often tuned jointly to achieve the same tuning goal. Those modules with dissimilar effects but interdependent, they should be tuned reference to previous modules in the pipelines to find a good trade-off balance. Our proposed method first decouples ISP structural knowledge and treats ISP tuning as a sequential prediction problem. It is effective to introduce sequence information and similarity relations in the high-dimensional hyperparameter space. Here is the overview of our method. Our proposed framework contains sequential CNN model and global similarity grouping. The sequential CNN model runs recurrently by predicting a group of parameters from several ISP modules, not all parameters, at each step. Meanwhile, the predicted parameters, along with the network's hidden layer and the input data, are in turn encoded as prior knowledge for predicting the following grouping of parameters. The global similarity grouping module divides ISP parameters into multiple disjoint groupings. The sequence order between groupings is explored heuristically using prior knowledge of the order of ISP modules. Given the flexibility, groupings are determined based on similarity among parameters, not limited to the same module parameters. The correlation of parameter activation maps learned through the model is used as the basis for parameter groupings. The global similarity grouping module runs once at the beginning of an iteration and partitions hyperparameters into T disjoint subsets. Parameters groups number T is less than or equal to the number of ISP modules. Some modules in ISP have similar roles. Grouping these similar parameters can reduce the model steps and make it more efficient for a large number of parameters and modules. We take the primal division as prior knowledge and use the correlation between parameters to explore the sequential divisions of parameters. To make clusters with sequence information, we introduce serialized initial clustering centers, CE to CT. The graphs that are adjacent and related in order are merged to obtain T-partitioned graphs, CE to CT, and CI is the vertex that is most closely connected to other vertices. With these initial clustering center, the clusters PE to PT are predicted in the sequential model. In this task, we use an existing sRGB dataset and a synthetic ISP to evaluate our hyperparametric prediction method. Since the input of the ISP is raw data, we processed sRGB images with raw data simulation. By comparing with existing methods, we can see that our method significantly outperforms. While the images produced by our expert tune ISP are more consistent with human perception, see the middle row, the images produced by our predicted parameters result in better performance for object detection tasks. These images have emphasized texture details and color features that are more in line with the preferences of the object detection compared to the expert tune images. In this task, we train the hyperparameter prediction network using the L2 distance between the RGB output and the reference image as the loss function. Compared with the exiting method, we have better PSNR and FSIM results between the reference image and the RGB output produced by the predicted parameters. It can be seen that our predicted parameters produce images with clearer texture details, better noise control, and human-adapted color features than the exiting non-sequential method. In order to verify the effectiveness of the sequence prediction results of the method, we tested the non-sequential and sequential methods under multiple settings, and the test metrics are the PSNR and FSIM results of the output and the reference image. The number of model running steps equals the number of parameter groupings. The sequential prediction results have better results than the non-sequential ones. To verify the effectiveness of the prior structural information of ISP, we changed the global similarity grouping by removing the block-wise sequence clustering centers and directly performing spectral clustering for all parameters. We also validated the effectiveness of this adaptive grouping approach. The results in table show the effectiveness of the prior structural information of ISP and the similarity grouping with the introduction of parameter correlation. In conclusion, a new sequential CNN structure to exploit the sequence processing knowledge within ISP. The potential sequential information among parameters is used to guide the processing of the model. We exploit the correlation among parameters by the proposed similarity grouping module. The flexible parameter groupings allow the exploration of cross-module relationships among parameters. In various applications, our method approach outperforms existing optimization methods and expert tuning. Thanks for listening.